In the vast expanse of mathematics, there exists a realm known as vector calculus, where we explore the intricacies of vectors and their behavior in space. Vectors, unlike their scalar counterparts, possess both magnitude and direction, adding a new layer of complexity to our mathematical explorations. Within this captivating domain, we encounter three fundamental concepts: gradient, divergence, and curl. These powerful tools allow us to quantify change, measure the flow of vector fields, and unravel the secrets of rotational motion. Imagine a world where we can precisely describe the steepness of a mountain, the flow of water in a river, or the swirling patterns of wind in a hurricane. This is the power that vector calculus bestows upon us. By understanding gradient, divergence, and curl, we gain a deeper appreciation for the intricate workings of our universe, from the smallest atom to the largest galaxy. In this exploration of vector calculus, we embark on a journey to demystify these fundamental concepts. We will delve into their definitions, explore their significance, and uncover their real-world applications. Through vivid examples and intuitive explanations, we aim to make these once daunting concepts accessible to all, igniting a passion for the elegance and power of mathematics. Join us as we unlock the secrets of vector calculus and discover the hidden language of the universe. The gradient, often denoted by the symbol nabla, is a mathematical operation that acts upon a scalar field, such as temperature or elevation, and produces a vector field. It tells us the direction and magnitude of the greatest rate of change of that scalar field at any given point. Imagine you're standing on a hillside. The gradient at your location points uphill, indicating the direction of the steepest ascent. The magnitude of the gradient tells you how steep the slope is. A larger gradient means a steeper slope, while a smaller gradient indicates a gentler incline. In mathematical terms, the gradient is calculated by taking the partial derivatives of the scalar field with respect to each coordinate axis. These partial derivatives represent the rate of change of the field in each direction. The resulting vector, formed by combining these partial derivatives, points in the direction of the maximum rate of increase of the scalar field. Divergence, denoted by the symbol div or ray, is a scalar quantity that measures the tendency of a vector field to originate from or converge towards a point. It quantifies the amount of source or sink present at a given point in the field. Imagine a water faucet. The water flowing out of the faucet can be represented by a vector field. At the opening of the faucet, water is being created or sourced. This is a point of positive divergence. Conversely, a sink drain represents a point of negative divergence where water is disappearing or sinking. Mathematically, divergence is calculated by summing the partial derivatives of the vector field components with respect to their corresponding coordinate axes. A positive divergence indicates a source, while a negative divergence indicates a sink. A divergence of 0 implies that the vector field is neither converging nor diverging at that point. Curl, symbolized by curl or x, is a vector operator that describes the infinitesimal rotation of a vector field at a point. It measures the tendency of the field to swirl or circulate around that point. Imagine a spinning bicycle wheel. The rotation of the wheel can be represented by a vector field, with vectors pointing in the direction of motion at each point. The curl of this vector field would be non-zero, indicating the presence of rotation. Mathematically, curl is calculated by taking the cross product of the del operator with the vector field. The resulting vector points in the direction of the axis of rotation, and its magnitude represents the speed of rotation. A curl of 0 indicates that the vector field is irrotational, meaning it does not exhibit any swirling or circulating motion.